you, Jules, and Philip for organising this. And thank you, Columbia, for last night's goal. It was fantastic. Yes, I'm going to give a little talk that follows on from what Clemens was talking about. And I'm going to talk about iterated games. But I'm going to relax two conditions that Clemens was talking about. One, that the game's state-free, and one that they didn't use co-utility. And I'm going to talk a little bit about how you can get rid of those conditions. But before I do, I just wanted to mention a couple of things. Firstly, for those of you who don't really know about open games but would like to know more, I'm giving an introductory talk to a workshop on Saturday called Strategic Reasoning. So if you want to know more about open games and generally, I'm going to give a talk there. That's based on a LIX paper, which is the sort of foundation for our work. So you can also read that if you want.
In fact, on Monday.
Oh, and
Monday I'll be talking at LIX.
Yes. So basically, I'm going to give the same talk as Jules, but I'm going to give it to the SR people.
Except you have 1 hour.
Ah, yes.
I have 18 minutes.
Right.
So wait, the strategic reasoning is part of this workshop? Or?
It's not part of this workshop. It is a workshop at Flock.
Oh, yeah, I mean, it's still in Oxford.
Yeah. It's basically people who do game theory but don't do category theory. So I'm sort of trying to go in there and say, this is what we do. Is it any good? Got any ideas? You know.
Otherwise, it's people that do game theory minus the people in this room.
There's 99.99% of the game theory community. You know. So yeah, so do come along to that. Also, I just wanted to say, so if you're interested in open games, we do a lot of this at Strathclyde. We'd love to see all of you. Some of you I know, some of you I don't. I'd love to get to know you. So if you're interested in anything to do with category theory, type theory, modal logic, functional programming, theorem proving, AGDA, dependent types, all that kind of stuff, that's what we do. So feel free to drop us a note, and we'd love to see you come up for a chat. Yeah. OK, so let me get on to what I was going to talk about. So in Clemens' talk, he wanted to start with the game G. And he made some assumptions. So Y, R, R. So he started the game like this. So notice that it's state-free. There's a 1 there. And notice that the co-utility type is the same as utility type. And he also assumes something else. So inside open games, there's a thing called co-utility. And co-utility basically says, you know, if I make some money from my utility function, I might pass on some of that to the environment. Because with open games, you know, where do you get your utility from? The environment has to give it to you. And so that's what the co-utility is. So assumptions, 1, state-free, 2. So in Clemens' work, to keep things simple, co-utility free. In other words, in the prisoner's dilemma that he was doing, whatever you get here, you just pass on. It's the identity function. And so that's what we meant by co-utility free, and I'm going to relax that.
Why do you think of the input as state? I thought that was such thing as a stimulus thing. You seem to have a different perspective on it.
So I think about, so the classic example I'm going to talk about, we're going to do this to model the dollar auction. And in the dollar auction, you have a bank account, and you have money in it. It's kind of like state. Whatever you want to call it. I mean, state can be used to model many things. But that's why I call it state.
In general, it's the stuff that your strategy can be contingent on.
Right, yes, I was trying to remember. I knew I had something to say. Thanks, Jules. So if you think about it, inside these game theoretic situations, you've got your strategies you can choose from. And you've got the state as well, like your bank balance or something. And when you first look at the definitions, they look very, very similar. They play the same role in the play function, the co-utility function, the equilibrium function. In fact, you think, why do I have these two concepts? Can't I merge them into one? And the reason you don't is because you can control which strategy you choose. I mean, that's the whole point about game theory, to pick one. But you don't get to pick your bank balance unless you're the Bank of England governor, I guess, or something. So they have very different roles. I mean, in some sense, one is demonic, non-determinism. you don't know what state it is, you have to deal with them all, whereas one is angelic, you get to choose. So that's why state is kept separate from strategies. If you like, strategies are, what's it called? Intentional parts of computation. Right. Now, when we're doing the, there it is. When we do the, when you want to do anything infinite, the modern way to do it is with final coalgebra, as Clement said. And so, of course, we want to do final coalgebras to study iterated games. Hopefully, one day we'll find a nice, snazzy coalgebraic automata, coalgebraic modal logic, bi-simulation argument, and we'll show it to game theorists, and they'll say, wow, cool, and then we'll be happy. I haven't quite got there yet, but I do want to have a discussion like I suggested before. I've got some ideas about where these things might be emerging, so if anyone wants to join in and see the technical details, please come along. But anyway, so, and then the final coalgebra we want is something like this, as Clemens explained. I mean, usually something infinite, like an infinite stream, or the final coalgebra, or the Kofi-Koman, I should say. Whenever you want to do anything infinite, you always end up solving these equations. The infinite stuff, or the recursive stuff, is one step plus some more recursive stuff. And you see that we're basically doing that kind of pattern here, but as Clemens explained, inside economic game theory, when you think about subgame perfection, we have this extra operator to cope with that. But it's basically what you'd expect. It's, you know, a one-shot game followed by carrying on playing it infinitely often. Okay, so therefore in Clemens's work, G infinity had this type. So we had still state free, and now in the one-shot game you get one y. If you play this infinitely often, you'll get an infinite number of y's. Fair enough. And then these stayed the same. Now, let's see what's going to happen if we start adding state in. So I guess what I want to do is say, unravel this isomorphism. So this becomes isomorphic too. So that I get one layer of G. So I have 1, I have y, I have R, I have R. And then I compose it with another game, that's this one, which is a bit like G infinity. So I'd have a 1 here, and a y infinity there, and an R there, and an R there. But even if you forget the economic intuition and just do the mathematical type checking, you notice these don't match up. So even from just purely type theoretic analysis, you want to actually have this game y arrow G infinity, because this operator puts a y there and a y there, and then they do match up and you can write the composite. And of course this is still y infinity. So let's see what happens if we put state in. So now we want to start off with some state. So this is the dollar auction. For those of you who want to know, the dollar auction is you have a bank balance and then you're playing it with somebody else, and each turn you take alternative turns, and at each turn you can either say, I'm going to play, which means I bet some of my money, maybe 5 cents, hoping to win that dollar. And then it's, or you can fold. If you fold, the other person gets the dollar. Okay. So the first thing you notice that, well, you know, if you've got a state and you play the first round of the game, of course your state's going to change. That's kind of the point about state. So that's not here in this picture. So the first generalization you realize is actually we're probably going to need an x here. So not only do we start with the g, but we also need a function which does the state transformation. So that's if you've got a state and a strategy, have a new state. So that allows us to build this slightly more general game. But now, of course, the composition doesn't really work either, because you've got this x here and it's only a y there. So there's a mismatch there. So, OK, what could you do? Well, this is, by the way, the structure of this talk is, well, you could do this, but it doesn't really work. And you could do that, but it doesn't really work, which mirrors our sort of, I think we spent about 3 months after saying, oh, it's all fine, it's all trivial, it'll all just generalize to, oh, it doesn't quite. And so I'm going to try and mirror that process to get you to the end. I saw a post on, I think it was Twitter recently, where it said that not enough people talk about failures. So this is 75% failure with, fortunately, 25% success at the end. Anyway, so you think, oh, well, why don't we put an x here? Because now they can match up. That seems fair enough. But where's this x coming from? Well, this, of course, this would be the state that you get after the first move. So of course, you know, we're going to have to track states at different times and moves at different times, so it all gets a little fiddly. So I'm going to make that very clear. So this is the state after move 1. Okay, so that can get passed on here. And then it looks very natural to say, let's condition our strategies in the following games, not just by the move that was played in the first game, but also by the resulting state. That seems fair enough, because you know, well, seems fair enough. And of course, now that we've done this, then there's an x that's been added there by this x times y arrow operator. And so that gets copied down here as well. So you see that the move that you got after the first stage gets copied here and then copied there. So that's move after state after move 1. God, that's there. And then, oh, I've got one state here. Well, you know, I'm playing this game iteratively. Actually, I'm not just going to be interested in the state after move 1. I'm going to be interested in all the states, the state after stage 1, the state after stage 2, the state after stage 3. So in fact, it looks like what we want to get is something like, oh, shit, I've mixed up my colors. So that's a good guess. If we're going to iterate our game, what we'll produce at the end of the game is a sequence of all the different moves that were played and all the different intermediate states that arose. So that seems fine. And that's what we thought, OK, we can just work with this structure. But it's not quite as easy as that. But before I talk about that, I'm going to discharge the other obligation, which I need to talk about, which is co-utility. So in this isomorphism, because it's an isomorphism games, you know, the play functions must be respected, the co-utility functions must be respected. So you can see that the co-utility function in your infinite game must be the co-utility function you get from this composite. And that allows us to write down a recursive specification of it. So what will it be? So the co-utility function right. Well, it's going to have to take, for the infinite game, it's going to have to take a state of that you play the infinite game in. That's our x. It's going to have to take a strategy. So a strategy, remember, will be a strategy for this game, and for every x and y, a strategy to continue with. So that's a sigma and an f. And it's going to have to take some utility that's given to you. Right? And then because the co-utility of the infinite game is computed recursively, we can say that breaks down into a composition of the co-utility here and a composition of the co-utility there. In other words, so if I've got my x and my strategies and my r, what r do I produce? Well, first of all, on the outset, outside, I use the co-utility of this game, and on the inside, I'll use the co-utility of that game. In other words, the co-utility for the infinite game on an... Oh, sorry, this was the type line, wasn't it? Right. In other words, the co-utility for the infinite game is computed using the co-utility of the top game. So I need to give you an x, a strategy, and an r. And I can give you an x. I can give you a strategy for the first game. I need to give you an r. So what r will I get? I'll get the r that gets passed from here. That's what I said. When you get repeated sequential games, the utility value here is what gets passed by co-utility from the subsequent game. All right, so let's do that. So that's C infinity. Right. So I need an x and a y. So I've got my x. And what's the y? The y, that's this y. That's the move we get played from this game. So that'll be a play function, dot, 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 some stuff. And then I need a strategy, which will be computed from f on the x and some stuff. And then the r, well, this r, if you remember, that'll be this r down here. So I can just use r. Now, I've not filled in the dots because they're not important for what I want to say. I just want to say that if you look at the form of this equation, you realize it's a recursive equation, obviously. It's not guaranteed to have a solution. So either you can do one of two things. You can either switch from the category of sets, work in some domain theoretic model where recursive equations always have solutions. That's fine. Or you can choose not to worry about it and say, well, if this equation has a solution, then we'll get our infinite game. So I'm not going to talk about co-utility anymore, but I just wanted to highlight the fact that the co-utility does get threaded, but it involves just recursive functions. Okay, so let's say we've chosen one of those two strategies for dealing with co-utility. So that's one of the restrictions Clements was talking about that we've dealt with, either by using sophisticated mathematics and domain theory, or by just saying that, well, for the game to be well set up, this is bound to have a good solution. Okay, so now let's get back to this. Well, unfortunately, this is not quite right either. Let's see if I can remember why. Well, the first state is missing. Because if you think about it, if you're going to condition what you do on this x, which remember is this x, which is this x, which is the state after move 1, what about the state that you originally start in? That's relevant. So then you start thinking, okay, well, perhaps I need to copy the original state as well, which is why I have to use all these colors and say, and remind you that we're going to have two states here. So this is the original state. Okay. Right. So what color do I want now? Let's choose black. Okay. So now they're matching up. We've got the state we've got the move played after the first game, the original state, and the state after the second game. So the state after the first stage game. Right. But then since I've produced another x here, you can see how mathematics gets frustrating. You try and push something under the carpet, and then it causes ripples and consequences later on. So now I have another x here, which is the original state. Now, of course, you could just fit this x inside here. You still have an infinite stream of x's. Up to isomorphism, this is what we had before. And now you think you're done again. We thought we were done because everything type checks. But actually, just because your code type checks doesn't mean you've written the right function. And for a long time we were thinking, oh, this is fine. But there's this nagging doubt. And here's the problem. You see, which x is this? If this x is the state after move 1, then, right. So this x, of course, comes because we've got this infinite game, which is stateful. And so as the infinite continuation, it comes with its own state. So this one should be the move after state 1, because it's the infinite game being played after stage 1. But then this one, the one that we're conditioning on, is also the state after move 1. So in fact, we haven't got, in this part of the code, we haven't got the two different states. Here, we'll be using two copies of the state after game 1. And similarly, and also that's not right, because if we want, let's say, this one to be the state after game 0, so that it gets copied down here, then we're going to be conditioning on state 0. So we've got a problem. We've only got one x here, and there's two states. Either way, things don't work out. So, right. Yeah?
You are over time, by the way.
Okay. Well, I'm going to finish very soon, actually, because so this was going to be a lightning talk, so it will finish very soon. Right. Now, there it is. So this stumped us for a little while. It was like so close. We've got the types work out, but the code's not really passing around the right variables. So what we realized, we actually have to generalize this this operator. So Clemens explained the use of that operator previously. Now I'm going to slightly generalize it. And that's all that this lightning talk is supposed to say. So I'm going to, right. So what we need to do is essentially take this state and copy it here. But we don't want to condition it here. So previously, whenever we use this operator, the A, it expanded the state and we conditioned upon it. But now we want the original state copied down, but we don't want to condition upon it. So that's our problem. So what we're going to do is the following. I'm going to define a slightly more general operator. So I'm going to take a game, an arbitrary game, and instead of conditioning it by the set A, I'm going to ask for a function m from B to A. And that's going to produce a new game. So like before, we'll take this extra information, we'll add it to the state, and of course we'll also copy that down into the future. So if this is going to turn out to be, part of this is going to turn out to be the original state, which will get copied as we wanted to. But now if I wrote a strategy as just B arrow sigma, that's exactly what we had before. I'm not going to do that. I'm just going to write A.
So this is like input information?
Yeah, it's about, you're right, it is exactly about, what information do you have access to, what do you do with it? So here, we're into the situation where we have information, previous states, previous moves, etc. But whereas previously we were forced to compute with all of it, that's actually not what we want to do. We only want to compute with some of it. So it's a lot of game theory is about a detailed analysis of who knows what, when, and what can they do with it. I think Tony Benn has a good quote about democracy. It's who holds the power, what can they do with it, and how do you get rid of them? And it's sort of a bit like that. Okay. Now that I've showed you this, as I said, this is a lightning talk. This is a very small tweak in what we had before, but it does allow us to solve this problem, so it's important. So therefore, it's one of those talks which is not going to blow your mind with new conceptual analyses, but if you want to do stateful open games, you realize this is required, and especially for those who are going to spend their lives doing this, it's good to tell them. Okay, so let's just see how this works. Does it work, this generalization? Well, what would be the play function for this game? So that's G. Let's call this m arrow G because of this function. So the play function, you'll take a state, that's a B and an X, and you'll take a strategy, that's an F, and now you have to produce your moves, so that's a B and a Y. Well, we talked about copying the B's, so that information is copied. We need to produce a Y, obviously we have to use the play function from here. So the play function from here needs a state, that's an X, which we've got, and needs a strategy. Well, F will compute a strategy because F has this type, but F needs an A. We've got a B, but M will turn B's to A's. So we can just do MB. And then similarly for the co-utility function and the equilibrium. If you see the trick here, that whenever you need an A to figure out what strategy you're actually going to use, well, previously you got given an A, now we're just going to compute it. So all the rest of the code is all the same. So that's all I wanted to say in this lightning talk. I wanted to do two things. I wanted to talk about how you treat co-utility, which Clemens didn't do because he restricted to the situation where you had the identity. And I wanted to talk about this operator, which is important to get the threading of all the different informations between states and moves. And so I guess going back to Heller's question in Clemens' talk, it's slightly confusing because you have because in our minds, thinking about this, we make the conceptual distinction between the X's, which is the state, the bank balance that's evolving over time, and the moves that are played. And moves, intuitively, in open games, aren't part of the state. But of course, you can model these things mathematically by shoving them into states and everything, so you do see moves turning up in the formal state parameter of an open game. Okay, that's all I wanted to say about this. I'm not sure there's really much to discuss about it, though. I didn't realize there was a half-an-hour discussion.